Right, so thank you all for coming. It's a pleasure to see so many people, and of course, there's a need for all of us to connect in these trying times. So today's talk is by Professor Eduard-Wilhelm Kirr from University of Illinois at Urbana-Champaign. Professor Kirr did his doctoral work at the University of Michigan, where he was advised by Professors Tony Bloch and Michael Weinstein. And after that, he became a Dixon instructor at the University of Chicago before joining the faculty at the University of Illinois, where he's been since then. And today he's going to talk to us about nonlinear coherent structures at the Fredholm boundary. Thank you.
Thank you very much for the invitation. It's my first time doing a seminar online, so I would like to apologize from the beginning for the mishaps that I'm sure will occur. So yes, I'm going to talk about nonlinear coherent structures at the Fredholm boundary. These are very general techniques that can be applied to many models. It's joint work with Vivek Natarajan, who is currently at IIT Bombay and a former student at University of Illinois, and Vlad Sadoveanu, who is currently my student at University of Illinois. And because these things can be applied in very general setting, I would like to illustrate them with an example. And the example will be the nonlinear Schrodinger equation, in which the derivative in time of the unknown function is equal to minus the complex number I, if you want, minus Laplacian plus a potential, that's the linear part applied to the unknown function u, and the nonlinearity plus a nonlinearity g of u, right? And the function, the unknown function, depends on time, on the space variable, which can be in any dimensions from n equal 1 to well, our hypothesis will kind of not be possible to satisfy them if you go very far, like n equals 7, 8. But I think it's good enough what we have for dimensions 1, 2, 3, 4, and 5, and 6. Oh, I'm sorry, this is the nonlinearity is defined on complex numbers with values in complex numbers. We are going to see that soon. So just forget about that. And the potential in modeling comes from external forces applied to this kind of physical phenomenon that can be Bose-Einstein condensates, or it could be water waves. So in Bose-Einstein condensates, it's external forces acting on particles. In nonlinear optics is the index of refraction, the linear part of the index of refraction that appears in the potential, for example. The potential I'm going to work with is decaying to zero at infinity, the way we kind of expect forces to have kind of a limited range of action. Remember that potentials can be chosen up to a constant, and so the constant that we choose at infinity is 0. We are going to assume a bounded potential, albeit that can be relaxed, and there will be some assumptions on the gradient of this potential. Now, I just wanted to remind you what happens in the linear Schrodinger equation so that we can move to the nonlinear one. The linear part, minus Laplacian plus v, is a self-adjoint operator on L2 with domain H2. H2 is the Sobolev space with two derivatives, right, in L2, and is a relatively compact perturbation of minus Laplacian under my conditions, under the condition that the potential decays to 0 at infinity. In that situation, the essential spectrum remains exactly as minus Laplacian, so it's 0 infinity, but the potential could add, kind of a compact phenomenon like a discrete spectrum in which the discrete spectrum is formed by isolated eigenvalues with finite multiplicity. And then by Stone's theorem, for example, we have that the dynamics in with initial data U0 in L2 is given by a superposition of these eigenvectors corresponding to the isolated eigenvalues. So this is the projection onto the eigenvectors, if you want, onto the eigenvector corresponding to eigenvalue W. The e to the minus I comes with from this I in front of the derivative in time. And then there is the dynamics on the projection on the continuum spectrum. And you know, clearly each of these is a periodic function with frequency omega, 2 pi over, or omega over 2 pi, depending on how you want to consider it. And the sum of them, if there are more than one, becomes a quasi-periodic function, but you know, which could be complicated, but it's kind of well understood. The projection on the infinite dimensional, if you want, space corresponding to the continuous spectrum could be much more complicated. However, it's been about 20 to 30 years that we know already that dynamics is decaying. So I just want to, we look at the projection onto the dynamics projected onto the continuum spectrum, and it's L infinity norm, it's decaying in time by a factor, well, by a power that depends on the dimension in which you are. So the higher the dimension, the faster the decay, right? So this is kind of the dispersion on the continuum spectrum of this operator. That's the reason it gives this decay. But you have, in this case, you have to start with initial data in L1. If you still want to start with initial data in something that looks like L2, you can use weighted spaces, you know, kind of a limiting example would be an initial U0 with compact support here, an initial data with compact support. Will have the property that if you remove the tails, this factor here will kind of de-emphasize the tails of the function U, the solution U. You have still the same type of decay in time. Actually, this is even nicer. This is without singularity at 0. You can see that this is singular at 0 for any n. And that's the second one is singular because an initial data U0 does not have to be in L infinity also. But immediately after you move a little bit in time, the function is in L infinity, the solution, and it has this decay. Good. So if you plug this back in to the solution that I just showed you, this part will decay in time. So this will survive. So you will be a quasi-periodic evolution that will involve projection on each of the eigenfunctions corresponding to the discrete spectrum of the minus Laplacian plus V. And that means that any solution of this linear Schrodinger equation decomposes into a superposition of linear bound states. And so we'll call those linear bound states. That's each of them is a periodic function that correspond to each eigenfunction, the sum of them becoming a superposition of these linear bound states. And there is the radiative part which disperses to infinity, or if you wish, it decays like this. Good, so now we want to move to the nonlinear situation, and in that case, we add the nonlinear function g, which is defined on complex with values in complex. We are going to assume that it's a C1 function over the real structure of, so it's real C1 and not necessarily holomorphic, does not have necessarily a holomorphic derivative. It has this symmetry that comes from most of the models that I have been listing in the first, I have listed in the first page. That's the gauge symmetry that the factor e to the I theta can be pulled around in front of the nonlinearity. And if you take the complex conjugate, you can pull it out. So it's equivariant. So the complex conjugate can act either on the input or on the result, and you get the same result. This immediately implies that that's why there was an F in the first page and I forgot to remove it, implies that G of U is of this form. It's of a function of a real variable where you will put the absolute value of U squared multiplying U. Yeah, so this has exactly these two symmetries, and every function with these two symmetry can be reduced to such a function. And so from now on, the conditions will be on F because it's cleaner to write them down in a sense. So, F will be, so these two conditions basically means, or one condition, it's here, basically means that it's bounded by power functions, and it allows us to show, for example, that this nonlinearity will take functions in H1 to functions in H minus 1. That's where these conditions are. That's why this. The reason I have two is that the behavior of S near 0 will be given by the smaller power here, say 1/2, so it will be kind of the square root function. And at infinity, it could be given by another function, which will assume that it's kind of power-like function. And this becomes very clear at the next level. So I'm assuming that as S goes to infinity, the f of S has an asymptote as S to the power P, if you want. So it behaves like the power S to the power P. Here, P will be a number less than P2 or equal to P2, if you want. And that limit is sigma, and it's negative, right? So one simple example of such kind of nonlinearity is the power nonlinearity. This is the function that will satisfy exactly this hypothesis with P equal this P in here, right? And in which case you can choose P1 and P2 to equal to P, and P has to be between 0 and 2 over n minus 2. Otherwise, the function will not, if it's higher than 2 over n minus 2, the function, the nonlinearity may not transform H1 functions into H minus 1, which is the usual spaces in which we work with this equation. So that's so I'm assuming a rather general nonlinearity with different behavior near 0 at infinity, but I need certain bounds to at least assume that G makes from H1, goes from H1 to H minus 1. Now, as for what will be the coherent structures, in this example, they are periodic solution in time like this, with frequency E here. And if you plug in, you will see that the nonlinear coherent structure, if you want, or eigenfunction, has to satisfy this nonlinear eigenvalue problem. And we know from the applications that, you know, these are usually called, because they are very much related with the potential, these special solutions are called nonlinear bound states. Bound states because they are kind of bound in certain locations of the potential. And they are one of the most important solutions in the application. They give, for example, the propagating modes in optical fiber. They give the shape of the Bose-Einstein condensates in Gross-Pitaevsky equation that corresponds to the Bose-Einstein condensate modeling, and or waves that propagate without changing shapes in water, changing shape in water waves. So what will be the asymptotic completeness conjecture that we actually proved via the Stone theorem for the linear case, that we would like to know whether any solution of any initial data for this equation, so the equation would be going back this one, any initial data, say in the energy space, let's start from H1, or even better if we need to, but it's not proven that we can show that any such initial data is going to evolve, as in the linear case, to a superposition of nonlinear bound states like these, nonlinear coherent structures, and the radiative part that will dispose to infinity. But there is one particular case in which for certain type of initial data, this is proven, and that's the integrable case, which via kind of a scattering transform, you can reduce it to a linear problem. That's dimension n equal 1 in space, right? So the psi e depends on only one variable, no potential, and the nonlinearity has to be the cubic nonlinearity and attractive. Sigma less than 0 will correspond to attractive nonlinearities. And we would like to understand, that's been an outstanding conjecture for a long time, if we can prove similar results in the nonlinear case. But I would say from the start, we need to know all these solutions, right? In order to know what will be the superposition that the initial data could look to and or could approach. And it's interesting that we know actually very little when the question about the solution of this problem is, can you find all solutions? Can you find a solution for each E, for example? I could have flashed. There have been a lot of results about the nonlinear eigenfunction or the coherent structure supported by this nonlinear Schrodinger equation. But the point is, none of the techniques, most of them are variational, for example, none of the technique can pretend that they are going to look for all possible solutions. They usually reduce it to a particular case, a particular form, and give no information what happens in general. So I don't want to, if you have questions regarding that, please, ask them maybe at the end. But I don't want to dwell too much into this. I would like to present you a new techniques that will probably, and I hope will, in my lifetime, let's say, solve at least the problem, not the asymptotic completeness, but at least find all the possible coherent structures. And then we'll see, depending what the initial data looks like, to which they might converge, right? Modular a radiative part that disperses to infinity. So the method I would like to show you is a bifurcation method. And for that, you basically reduce the problem to finding zeros of a certain map. My map will be between two Banach spaces. One is the dual of the first one. Yeah. The zeros are the zeros of this F. If you look back, well, with one other mistake, as I said, here should be G of psi by itself, but one example of G of psi is exactly this power nonlinearity. So what we have is the eigenvalue problem in which minus E phi has been moved to the right, so the result should be 0. So if I find the zeros of this function, and this function is well defined between H1 cross R is the eigenvalue parameter with values in H minus 1. So if I find the zeros of this map, and if I find all the zeros of this map, I'm done. I have found all the coherent states. Now, this particular problem has symmetries that sometimes help, sometimes makes the problem more difficult. So it's invariant under the multiplication, or equivariant. It pulls out under the multiplication with e to the I theta, or taking the complex conjugate, right? So this function is real on reals. It takes a real valued function into a real valued function. Oopsie, that's not what I wanted. I forgot that my laptop is very sensitive to touching things. So in particular, I want you to realize that if I find a coherent structure, a solution psi EE, and I rotated it, I get a new solution because of this condition here in equivariance under rotation. And by my assumption that the nonlinearity here will be a C1 function over the reals, if I work over the reals, so I'm looking at functions, psi, if you want, that are in H1 defined on Rn, and with values in complex numbers, I look at the real and the imaginary part of them. So I do the representation of this space as a Cartesian product of this. I'm getting, so this will be with the real structure, then this will give me the fact that the function is C1. So we can use local bifurcation theory or other theories that depend on having a kind of a smooth nonlinearity. For me, the nonlinearity is just C1. It's not smoother than that. But C1 is good enough, for example, to start with what I call the ground state. So what's here, minus E0 would be the lowest eigenvalue of minus Laplacian plus V. And I'm assuming that it does have, so V is significant enough to pull at least one eigenvalue when it's added to the Laplacian. So this is back to the linear theory, right? And the reason here I'm switching, if you looked at the equation, I was switching from e to the minus I omega t to be the periodic function to e to the plus et. So e is minus omega here. So that's why E0 is positive. And if I were to have the linear equation, the ground states or the eigenfunctions corresponding to the eigenvalue minus E0 would form a two-dimensional space here. It's only one dimension represented. H1 is just a line. This basically my drawing talent kind of stops there. That's why probably I'm working in more abstract problem than I should be working, but it's because I cannot draw too well. Then this would be, remember, for a linear problem, an eigenfunction can be multiplied by any scalar, so it's at least a line, right? And because I have removed the other direction, the imaginary part, if you want, I can see only a line, but it should be a plane, will be the solutions of the linear problem. And in time, they just rotate in that plane, which you cannot see here, but it's a rotation around this axis. That will be a representation what happens in the linear problem. Now you can see in the nonlinear problem with an attractive, essentially attractive nonlinearity near zero, the nonlinear eigenfunctions kind of come from the tangent from the plane of the linear eigenfunctions, but they are bended. Right? And this is a rigorous theory, at least in a small neighborhood, and that's what we know, the only thing that we can infer from local bifurcation theory, that in a neighborhood of E0, there is this kind of curve that will be actually a parabola, if you want, if it's exactly the cubic nonlinearity. And the rotation of that curve, as we discussed, is the manifold of all coherent structures in a neighborhood of this point, right? So in the point 0 in H1 and E0 in eigenvalue, in the real numbers, yeah? So this is kind of old results, at least 30 years back. Now the question is, when it was the linear problem, this manifold can be extended by just multiplication by scalar to in both directions. It's a full line, and then by rotation, it's actually an entire plane. This is just a small kind of branch in a neighborhood of E0. So the question is, that plane got a little bit bended locally, but then wouldn't be to large solution linear, wouldn't we have maybe large solution corresponding to the nonlinear problem? More precisely, can we continue this beyond the local bifurcation theory to find maybe all the coherent structures that connect to this branch that emerges from E0? And actually, the answer to that question, I would like you to understand that it's positive. We can do that. But the methods that we are going to use are not very well known, and they rely on the global bifurcation theory. This is not, I'm sorry to have to say this, this is not what you will find in Wikipedia. They are wrong about what global bifurcation really is about. Global bifurcation exactly answers this question. You have maybe a branch or a certain manifold of coherent structures or zeros, let's say that, zeros of a map that's maybe smooth or non-smooth, or satisfy certain hypotheses. Can you continue that branch? So can you found the connected component of the solutions of these of the zeros of this map that contain that initial point 0 E0 from which the branch emerged? And the answer is that that branch cannot actually just stop dead somewhere. It has to reach the boundary of the domain where the linearization of f with respect to the unknown function, with respect to the zeros, the coherent structures that we are looking at, is Fredholm. So the domain where this linearization is Fredholm, that means the kernel of the linearized operator is finite dimensional if it's not trivial, right? And where the range of the linearized operator has finite codimension. So the space that you have to, maybe orthogonal, since we are working in Hilbert spaces here, the orthogonal space to the range is also finite dimensional. The other alternative, if it doesn't reach the boundary of this Fredholm domain, the other alternative will be that it forms a loop. Let's put it this way. It's written in a different way because that's how Rabinovich, this is a result by Paul Rabinovich in the 80s. It relies on the fact that f only has to be continuous, but a little bit more than that. It has certain compactness properties, right? So it's a kind of, when you rewrite the problem with the correct operators, inverting some of the operators, that it's like minus Laplacian plus identity, what you get, it has to be a completely continuous or compact, completely continuous as a nonlinear operator. And in order to define a degree for this problem and use degree theory to find the zeros. I don't want to dwell too much into that. And the main reason being that as long as I put an attractive nonlinearity in my example, that compactness is very hard. Actually, it's unproven at this moment. If you put a repelling nonlinearity, so you change the sign of sigma to make it positive, then there are interesting results of where this branch ends. And these are the citation. It's 3 papers that Jean is co-author to all. Dancer is in some of them. So they are in the 1990. All of them were published in 1990. This kind of results. I could say one more thing. In this case, what happens in this case, when it's essentially repelling the nonlinearity, the branch kind of turns the other way. And what they show is that it actually has to reach the point E equals 0. E equals 0 is one of these Fredholm boundary, because for E negative here, the linearization, you are in the continuum spectrum of the linearization. The linearization looks like a Schrodinger operator, even for the nonlinear problem. The linear part of G of the nonlinearity behaves like another potential, and it's still a potential that's relatively compact under my assumption on G, relatively compact with respect to the minus Laplacian, which will make from 0, because of the change of sign that I talk about in between minus omega and E, the continuum spectrum is from minus infinity to 0. So this is a boundary. This is what I call a Fredholm boundary. And the other Fredholm boundary for this problem, so when you linearize anywhere here, that means an H1 that's arbitrary function and an E that is strictly positive, you can actually show that the linearization is Fredholm. So this is the Fredholm domain. And for repelling nonlinearity, Jean and the others and co-authors show that the branch actually ends at E equals 0 at this boundary. Now for attractive nonlinearity, what I'm going to show you is that this branch ends at E equal infinity. The boundaries are now E equal infinity or norm in H1 being infinity, right? Both of these points correspond to H1 norm going to infinity. So I will show, for example, that there will be no limit points. This branch cannot approach a finite E, and the norm in H1 goes to infinity. And it cannot turn around and then approach E equals 0. It will stay always to the right of the point E0. So that's the idea of how we could combine now the global bifurcation theory with an analysis, and that's my point of the talk. So global bifurcation theory has been around now for probably 20 years, but it's not very well known and probably not very well used because it just tells you that these branches that you can construct by local bifurcation theory, that's, you know, a lot of work has been done in that direction, local bifurcation theory, I mean, these branches end up at the boundary of the Fredholm domain. So, or form a loop. Again, this second situation is form a loop. What I'm trying to propose to you is that what if we can find every branch that's at the boundary or converges or approaches a boundary of the Fredholm domain or the boundary of the Fredholm domain? What if we can find all? And in that case, we have a lot of information. We know where every branch that does not form a loop, so my theory will never probably catch those that don't form a loop. We have information where they end, and maybe, and you will see numerical results, we can backtrack them from their limits at the Fredholm boundary down into the Fredholm domain. And at least then in the Fredholm domain, we can find all the coherent structures. By the way, for my example, there are no coherent structures that are outside the Fredholm domain under kind of assumptions like if they were to decay sufficiently fast, then they cannot be they cannot correspond to negative E's, which will be they correspond to kind of linear eigenvalues that are in the continuum spectrum. Right? So this is what I just said. It's a kind of an old result by Lyon. So what I'm trying to say that at least for my example, if I found all of them in the Fredholm domain, and I'm not going to completely finish in this talk that discussion, but if I can find at least their limit points at the Fredholm boundary, that maybe I can move down and find, track them from those limits and find them all in the Fredholm domain. So that's the idea of the talk. This is the Fredholm domain for me, and let me just be much more precise. I'm not going to use the result by Rabinovich, so I'm not going to use topological methods for global bifurcation, but I'm going to use the analytical method because it requires less compactness. You see here there is a condition on the compactness. Again, it says the same thing, that actually any branch that you can start from, if F is real analytic, can be analytically continued. So we are looking for the zeros of F, right? Now it's a lot of smoothness. It's real analytic, capital F. But in that case, you can analytically continue any branch that starts at any branch that you can construct via local bifurcation technique up until it reaches the boundary of the Fredholm domain, or it forms a loop. Here it forms a loop. Right, so besides the one that form a loop, they have to reach the boundary of the Fredholm domain. Now, I meant to explain a little bit why this compactness is important and why can't we get it for our problem. Well, we can get this one, that's the theorem, but it's much, you know, it's not the full compactness of the operator F. It's just that the connected component that you are looking at is relatively compact. That's useful. So you only have to study compactness for solutions of the problem, not compactness of the full operator. And because they are solution of the problem, we can use certain techniques to prove this theorem. This is a non-trivial result. This is the result that kept us for years up until we were able to prove it. And it probably now has around 60 pages of proofs, and it's kind of hard to publish, but the paper is available. And it's just an intermediate result so that we can apply this analytical maps method. Again, I don't want to enter in details. This compactness, if it's missing, nothing that is said here might be true. So it's an essential condition on the analytical continuation method, and a stronger version of it was essential to use topological degree. Otherwise, you don't even have a degree well defined for those maps. So, but I'm not going to dwell into that. These are results by Dancer, for example, so and Buffoni. Let me move to the results that I have been working with my students. And what this theorem tells you exactly is what happens at the E equal infinity boundary. So E here goes to infinity. So the global bifurcation theory for analytic maps can be applied. So let's say I'm assuming that my nonlinearity is real analytic at this stage instead of just C1, but I only need C1 smoothness for everything. So by local bifurcation theory, all the branches that emerge from a C1, all the zeros of a map that is C1, they will be C1 in certain parameterization. Not necessarily in E, but in certain parameterization, they will be C1. What this theorem says is that if there is a branch approaching the E equal infinity Fredholm boundary, it has to respect certain growth, if you want, of the norms. These are the important norms that appear in the energy formulation of the example and will correspond to the energy formulation of other examples if it's not the Schrodinger equation that you are looking at. But it's essential that this behavior, which can be shown basically by ordinary differential type techniques, you look at how these norms evolve in parameter E, for which you can differentiate with. So this is real on real, right? So that's a norm, right? So the parameter is E, so this is a map from E to some real number, and you use ODE techniques to kind of determine this behavior. And this behavior uniquely determines a change of variable that you can do in order to keep the psi E norm, for example, the H1 norm, which is dominated by this, the gradient of psi in L2, blows up. See, if you look at what P can be, that's the P that was in the hypothesis, in the last hypothesis about the nonlinearity. And because it's less than 2 over n minus 2, you will see from this that E is positive. This goes to infinity, actually. So divided by something that goes to infinity 2, it gets a finite number, which is this. And together with the other estimates, this is the only change of variable. It determines the parameter here, the parameter here. This is the only change of parameter of a function, if you want, which will keep this solution that approach the E equal infinity boundary, will keep them bounded in H1. And now once they are bounded in H1, we know from concentration compactness that they could converge to one function, or they can split into many profiles of functions that have the support basically separating from each other. And this is exactly what the result says, that this solution can actually split in finitely many parts. This sum is finite, of profiles. Each profile here is centered somewhere else. You see that as e goes to infinity, the distances between the profiles and 0, for example, goes to infinity, like square root of e, or differences between different profiles here. If you do that, you'll see that will always go to infinity. The sum is finite and it's convergent. The convergence is in H1. So the rescaled, renormalized solution converges to a sum of profiles of solution. Each of these UK is a solution of a different problem. Well, it's the same problem basically, but E is equal to 1 and the potential has disappeared. So the limiting equation, if you want, is a simpler equation. It's a constant coefficient equation. There is no potential that depends on X anymore. And if you have good information about the limiting equation, you can actually have very good information about the limiting points at E equal infinity. And here is some of them. The one that you can do in general is that this center, if you want, of the profile, the center of the profile either diverges to infinity, or if it converges, it must be at a critical point of the potential. So even if the potential has disappeared, it does still count by forcing this profile to basically localize themselves at the potential. So if you change the variables back, be careful here. If you change back, the actual profile grows in amplitude, but concentrates at a critical point, concentrates exactly at xk, at a critical point of the potential. It will look like Dirac kind of approximations of Dirac functions, but you will see some examples in a few minutes, maybe not so many minutes, in a couple of minutes, okay? So that's one result. The second result is whether there are, this is assuming that such a branch exists, then it has to have the properties. Question is, do they exist? But the theorem says that if they exist, we know where to look for them at critical points of the potential with a profile that looks exactly like the solution of this problem. And even this problem, you know, it's not completely solved. We don't know all the called excited solution of this, but the ground state of this problem is known, and it's, you know, for probably around 20 years also. Usually variational methods are used for that problem, but you can show that it has a unique radially symmetric positive solution. That will be the ground state. And if you are looking only of the coherent states that are ground states, by that I mean, okay, the ones that are, you know, up to a rotation, they are real valued and positive. Let's just say that's my definition of what a ground state is. But of course, at the limit near E0, as I showed you, that's actually the minimizer of the energy functional if the nonlinearity is L2 subcritical, for example, but let's not get into those details. So it's related to the minimizer of the energy for good nonlinearities. For bad ones, it's related to minimizing or other type of functionals. But in this case, by some assumptions, like looking for positive solutions of the problem, I restrict the type of limits that you can find, UK, it has to be a positive solution of that. There is only one of that up to translation and rotation, and that's the ground state of this problem. And with that extra information and, you know, the decay properties of the ground state, we can actually show that the profiles cannot diverge to infinity. The center of the profiles cannot diverge to infinity. It requires a little bit of more decay assumptions about the potential at infinity. For example, let me just say this: I cannot use a compact potential, a compactly supported potential, because the decay at infinity is then, it's zero nearby at infinity, and I cannot exclude that in this case I have solutions that diverge to plus infinity, for example, profiles that diverge to plus infinity. But you know, I can talk more about these decay of potential assumptions if they are very mild. And for example, you can use, I apologize again, you can use power kind of decay, like in the Coulomb potential. You can use exponential decays. They all work to show the result that basically you, for ground states, you only, so for positive solutions, psi e, you only have xk converging to critical points of the potential. And then you have the opposite theorem, or the reciprocal, if you want. If you start from a distribution, if you want, of profiles at each critical point, there is exactly one curve modulo rotation. It's one curve, but it will be a kind of a parabolic type of rotational surface of solutions that emerge from that limiting point at E equal infinity. Right, so we have this extra theorem, and since the time is kind of running out, let's see how we can combine these two of them for a double well potential. I just want to remind that you take one potential and you translate it in one direction and then in the opposite direction. So for example, along the x1 axis, if you are in Rn, here is we are in R, x is only one dimensional. So I translate it to the right and then take the mirror image to respect to the x equals 0, and I get the double well potential, right? I add the two, the mirror image plus the translated, and I get the double well potential. And the spectrum of the double well potential can be understood, at least in the limit, when the distance between the wells goes to infinity, which means how much you translate this to the right before you take the mirror image. You can understand the spectrum of that. So we have a lot of information about these double well potentials, but important is it has three critical points, two minima and a maxima, right? And this theorem says that that's where I should look for these limits of my branches that go to E equal infinity. So that's it. I have three critical points. I can have a profile at each. So one profile, two profiles, three profiles. These are the symmetric, you know, the double well potential, the way I construct it has this mirror symmetry. So x1 going to minus x1, for example. So these are the ones that respect the symmetry. These are the ones that do not respect the symmetry, right? And so from such, this is a profile localized at the maxima, which is 0. This is two profile localized at the minima. If you want the symmetric ones, you have to, if it's localized one profile at the minimum, the same profile has to be localized at the other minimum. And this is the one that has a profile localized at each, right? These are the only solution of my problem, let's say. That's the theorem says that if it's one profile at each critical point, that's the solutions that come out. What I said about studying the linearized operator, because this is a local bifurcation theorem, even if it comes from infinity, it's still a local bifurcation result. I can calculate the number of negative eigenvalues of the linearization. I can do them as the branch emerges from 0 at E0. And now the global bifurcation theory says that this one should end at one of these limits, E equal infinity, which is this one, E equals 0, which I told you I can show it doesn't happen, or E finite H1 going to infinity. This is N here, so H1 norm going to infinity will mean also that the L2 norm will go to infinity. We can show that for this particular problem. And that doesn't happen. So, and we can also show that this one doesn't form a loop, doesn't do this. And so it has to connect to one of these, right? Let's forget about the non-symmetric one. Let's say it connects to the first one. If it does that, just look, the number of negative eigenvalues switch from 1 to 2. So you must have a bifurcation that will happen regardless to what it connects to. So if it connects to the first one here, you have this picture. there is one bifurcation along that branch. So it's not as simple as in the linear problem that you just bend the plane and you get the surface that gives you the nonlinear eigenfunctions. It's kind of, they have bifurcation in them. The rest comes from the fact that this one cannot form a loop because it's only one solution coming from here. And so it has to turn back to the other one. And so it cannot end here, cannot end here. It has to end back at equal infinity. That means there will be two bifurcation here going from 2 to 4, a number of negative eigenvalues. And then you can construct, you see each of these bifurcations, some of them will generate non-symmetric states, some of them symmetric. Now you look at what are the non-symmetric states that you can end up with, and there is only one way that they can be connected. So by just assuming that the branch at E0 connects to the one here that's localized at maxima, we are getting this picture. And that's the full picture of all the ground state. Let's see. There is an almost that I can explain. This will be another case when one connects directly to this one. So there will be 4 bifurcation along here in order to move the eigenvalues, 3, I'm sorry, from 1 to 4, to move 3 positive eigenvalues into negative eigenvalues. So that's why you have this kind of distribution of the bifurcations and the other states that emerge from them, right? Again, there could be loops forming of these branches. I cannot deal with loops because they do not end at the Fredholm boundary, and I have only studied the Fredholm boundary. So let me kind of give you some conclusions here because I'm out of time. So the reason I haven't spoke about some interesting phenomenon here that we still have to understand. Let's just say that for my example, we know how the number of critical points, and we can do this analysis for 4 critical points, 5, like 5 will be, for example, triple well. We can do this analysis again and again. And so the result is that we are going to produce all the coherent states manifolds that reach the Fredholm boundary. We are going to miss the one if there are any, but numerical simulations that we did up until now suggest none. Manifolds that form loops. And for general nonlinearities, so this is valid if you use only the pure power, or even if you use a finite sum of powers, then we can say that there are no branches that approach, that blow up at finite E, if you want, or approach E equals 0, right? But for general nonlinearities, these are still kind of opens, and here I'm talking about general nonlinearities that behave attractive at large data. The limit that f of s over s was, or s to the power p was sigma with sigma negative. So those type of things will have all these results that I told you about equal infinity. But if it's a general nonlinearity, we are still having trouble excluding the case where the branch can blow up at finite E. And if it does blow up, who are the limit points, and do we get bifurcation? So we have general results about, all the other. For example, if the E0 branch will just blow up at finite E, will it still have bifurcation like it had in all the cases in which it was not blowing up, it was going to equal infinity? So that's what we can do to this problem. And I just wanted to mention that the techniques I was using in order to get these results are related to energies, estimates, to analysis of the linearized operator concentration, compactness kind of results, and properties of the limit equation in various regime equal to infinity, or the H1 norm going to infinity, was inside the proofs that I haven't shown you. And we can redo that for any other problem, of course, with different results. The different result, for example, if I do repelling nonlinearity, will be that now everything goes, for example, to the E equals 0, which is the Fredholm boundary past which the differential operator, the linearized operator is not Fredholm, the kernel now is infinite dimensional. So that, that's a point that it's a little bit more difficult to study. Thank you. I will stop here.
All right. Thank you, Professor Kirr. So